Okay, students, in this clip we're going to be going over how to carry out rectangular approximations. We're going to be doing the left endpoint rectangular approximation and the midpoint rectangular approximation in this series. And this is just a part of a multi-part series getting you ready for your integration test, okay? Alright, so with that in mind, let's go ahead and take a look at question number one. We're going to be using the TI-89 to assist us in solving these problems, but you can use any calculator to do these problems, okay? Alright, so in question one, I write this down. The task is to use R, LRAM. LRAM is left endpoint rectangular approximation, okay? Use LRAM to estimate. So estimate the area under y equals negative x minus 5 squared plus 4 on the interval, the closed interval 3 to 7, using 8 subintervals. Okay, using 8 subintervals. And you expect it to include a sketch. Alright, so in this problem, we're going to start out by sketching the curve. That's basically one of the most important pieces of the whole graph is to get, the whole problem is to give ourselves a good visual representation of the situation, okay? So let's go ahead and sketch what this graph looks like. We're going from 3 to 7. So we can make a table of values and calculate what the output is going to be, okay? So you can use a calculator, but let's just do it by hand, assuming we don't have a calculator. So let's calculate what the output values are. We're going to start from 3 and go all the way to 7 because that's the interval under consideration, okay? Alright, so let's populate our table in the following fashion. X and y equals negative x minus 5 squared plus 4. And then our output is going to be y, okay? Alright. Alright, so let's start out with 3. So we'll plug in 3, giving ourselves a little arithmetic practice here. We'll plug in 3 into the function. Y is going to be negative 3 minus 5 squared plus 4. 3 minus 5 is 2, square is 4. So it's going to be negative 4 plus 4. So our output here is going to be 0. 3 goes to 0. And then the next one is 4. I'll plug in 4 into the function y equals negative 3 minus 3 minus 4. 3 minus 3 times, in parentheses, 4 minus 5 squared plus 4. So 4 minus 5 is 1. Square is just 1. So it's going to be negative 1 plus 4, which is 3. Output here is 3. And then for 5, we're going from 3 all the way to 5. All the way to 7. So we'll plug in 5, we get y equals negative 5 minus 5 squared plus 4. Okay, 5 minus 5 is 0. Negative 0 plus 4 is just simply positive 4. Okay, output is 4 for the input of 5. Alright, we have 2 more inputs to consider. Makes it a little bit longer. And then we'll go ahead and use those points to sketch our graph, okay? Alright, so we're going to take a look at 6, which is the next number. So if we plug in 6 into the function, we're going to get y equals negative 6 minus 5 squared plus 4. 6 minus 5 is 1, so we have minus 1 plus 4, which is 3. So output here is 3. Notice that there's a symmetry going on here with our quadratic function. And then we plug in the last one, which is 7. And we'll have y equals negative 7 minus 5 squared plus 4. 7 minus 5 is 2. If you square that, you get 4, so you have negative 4 plus 4, and that equals 0, so you have 0. Alright, so there you have it. Okay, so what we're going to do next is we're going to go ahead and sketch the graph, and then we're going to generate a visual as to what a left-handed rectangle approximation looks like, okay? Left endpoints. So we notice let's look at our range. The x's are positive. It goes from 3 to 7, and then our y's go from 0 all the way to 4. Alright? So since we're using 8 subintervals, let's go ahead and make a sketch. It's good to use 2 tick marks for your x-axis calibration, so just in case you want to use a midpoint, okay? So there goes my x and my y and my x-axis. Alright, so just to make it sufficiently large, I'm gonna let 4 tick marks be my units, okay? So this would be 1.51, 1. I don't think I have enough space. Let me allow 2 tick marks to be 1. Okay, or else I'm going to run into problems here. So let's call this 1, 2, 3, 4, 5, 6, 7. Okay, that's the range for my x. And then for my y, I'm just going to go all the way up to 4. So let's call 2 boxes 1, 2, 3, 4. Okay, so that's how high my parabola is going to go. Alright, so let's go ahead and graph the points. You note all these we can do using a graphing calculator. Okay, I'm just showing you the manual process of generating the curve. Alright, so for 3 goes to 0, so we have a point here. 4 goes to positive 3, jumps up to here. 5 goes to 4, up here. 6 goes to 3, right here. 7 right back to 0. Okay, so we can sketch the parabola as best as we can through these points, like this. Remember, this is just a sketch. There, there. So what we're trying to do in this problem, that's the point, is estimate the area under this curve using the left endpoint rectangle approximation. Okay. So let's give ourselves a visual as to what it looks like. Then we're going to use the tools of calculus to generate what the actual approximate value is. Okay. So if we're using left endpoint rectangle approximation, so we're going to be putting rectangles into our intervals right here. Okay. So how many intervals do we have? 1, 2, 3, 4. 4 intervals going by units based on this spacing. All right. Well, let's take a look at the problem. The problem asks us to use 8 sub-intervals. Alright? So what does that mean? That means that we're going to have to split each interval into 2 in order to have 8s, because we have 1, 2, 3, 4. So we have to split it into 2. Okay? So since it's left endpoint, we are going to let the left endpoint of our rectangle touch the curve. Okay? So to do that, what I'm going to do is let me mark my points. Starting from the left, this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, I started from the left endpoint. So these are the x values that I'll trace to my curve to generate my rectangles. Okay. All right. So this point right here is already on the curve. So technically there's a rectangle here. We're going to trace this point up to here. Straight here, we're going to draw a rectangle here. This point traced up here. There's going to be a rectangle there. This point traced up to this point, there'll be a rectangle right there. This point, I'll trace it up here. There'll be a rectangle there. This point up to here, there'll be a rectangle there. This point up to here, there'll be a rectangle. And then this point up to here, there'll be a rectangle. Okay? So let's go ahead and sketch our rectangles. The first one, remember, is the left endpoint that touches. Okay? So this one is just going to be a flat rectangle right here. There's a rectangle of 0 area. Okay? And then the next one is going to go up to this point right here. Notice the left end point. That's not that area. And then the next one goes straight up here, the left end point, and then expand it and make a rectangle. And then the next one starts from here, the left end point touches the curve, and then complete it like that. And then the next one, the left end point touches the curve, half a unit wide. The next one, the left endpoint touches the curve, half a unit right. And then the next one, and then the next one, the left endpoint touches the curve. And then the last rectangle. Okay. So you notice that only the left endpoints were touching the curve. So we have 1, 2, 3, 4, 5, 6, 7, 8. These are our 8 rectangles. Okay. That represents what we're looking for. Now, since we had to break each interval into halves, that means the width of each rectangle is going to be 1/2. Okay, so each rectangle will have a width of 1/2. Okay, I hope you can see that because the whole thing is 1 unit. So each rectangle will have a uniform width of 1/2. Okay. All right. So what is the left-hand rectangular approximation going to look like? We're going to be inputting the values of our left endpoints. Okay. And the values we're going to be inputting, we started from 3, so we're going to be using 3. The next one is 3.5. The next one is 4. The next one that we're going to use is 4.5. And then we're going to use 5. And then the next one we're going to use is 5.5. And then the next one we're using is 6. And then the next one is 6.5. And we're done. Notice we have 1, 2, 3, 4, 5, 6, 7, 8. It has to be 8 of them. Okay, these are the x values that I traced. So when I input these x values into my curve, it tells me the height of each rectangle. Okay, this tells me the height. Obviously, when I plug in 3, I get a height of 0. Okay, and then I have to plug in 3.5, 4, 4.5, 5, 5.5. By inputting these values, I get the height. Okay, so let's write down an equation. So for this one, the left-hand rectangular approximation is going to be, since all their heights are the same, well, let me show you the whole process so you don't get confused. Okay, so we know that the area of a rectangle is length times width, right? Length times width. So the first rectangle is going to be, the width is 1/2. Remember, all the widths are 1/2. 1/2, and the height is going to be f of the left endpoint, f of 3. Okay? Plus, move on to the next one. It's still going to be another 1/2 because all the widths are uniform, times, 1/2 times f of 3.5 plus 1/2 times f of 4 plus 1/2 times f of 4.5 plus 1/2 times f of 5 plus 1/2 times f of 5.5 plus 1/2 times f of 6 plus 1/2 times f of 6.5. Okay? All this is length times width, length times width, length times width, length times width. Okay? So this is the first rectangle, second, third, fourth, fifth, 6th, 7th, 8th. The width is 1/2, the height is f of whatever the x value, the left endpoint is. Okay? Notice this is a longer, tedious way of writing it. Since you're evenly spaced, anytime you have evenly spaced a rectangle or approximation, you can just factor out the width, uniform widths, right? So I could have written this whole thing as 1/2 times 1/2 multiplied by f of 3 plus f of 3.5 plus f of 4 plus f of 4.5 plus f of 5 plus f of 5.5 plus f of 6 plus f of 6.5. Okay, this is a quicker way of writing it. You can write it this way since they're all uniform widths. But if the widths are not uniform, then you have to actually write it out the long way and calculate each area independently. Okay, so I hope this helps you understand how this formula came about. I just factored out the 1/2, which is the width of each rectangle. Okay, all right. Now, what we're going to do, why don't we use a calculator to calculate what each of these values are, and then we'll see what our final result is. Okay, so instead of wasting my time doing everything over and over again, I'm going to use the table function of our graphing calculator. Okay, so let's go to the Y menu. Okay, that's the Y menu. See. Alright, my calculator had a little glitch there. Sorry about that. So what I'm going to do is I'm going to enter the original function into my calculator, and I'm going to use the table option to generate what the outputs for these input values are. Okay, so we have negative x minus 5 square plus 4. Enter. So I've entered my function. You can do this in any calculator, any graphing utility. Okay, so I'm going to go to my table. Menu. So I have it set up weird. So let me go to my table set. Tables start at 3, and the delta for my table, I want it to change by 1/2. You notice that my increments is by a half, so 0.5 for the delta of my table. Save that. All right. See, these are the output values I'm looking for. Okay, so see. Okay, so these are the values I'm going to be using. Okay, so for 3 we have 0, for 3.5 we have 1.75, for 4 we have 3, for 4.5 we have 3.75. So these output values, I'm going to copy them right here. Okay, so let's go ahead and write them down from your calculator. So from f of 3 is 0, plus f of 3.5 is 1.75, plus f of 4 is 3, plus f of 4.5 is 3.75, plus f of 4.5 is, this is 3, 3.5, 4, 4.5, f of 5 is 4, f of 5.5 is 3.75, f of 6 is 3, f of 6.5 comes down to 1.75. Okay. All right. So these are the output values that we got from our calculators. Okay. So let's bring that up again so you can see. So 3 goes to 0, 3.5 goes to 1.75, 4 goes to 3, 4.5 goes to 3.75, 5 goes to 4. Scroll down. 5.5 goes to 3.75, 6 goes to 3, and 6.5 goes to 1.75. Okay, this is the right endpoint. We don't need this. All right, so this is just a shortcut to calculate outputs of a function if you don't want to keep doing the same procedure over and over again. All right, so what we're going to do, let's have our calculator help us finish this off. So what we're going to plug in, let's go back to the home screen. We're going to do, let me print this. This. My home screen, so we're going to have 1/2, in parentheses, 1 divided by 2 times 0 plus 1.75 plus 3 plus 3.75 plus 4 plus 3.75 plus 3 plus 1.75. Enter. Our answer is 21/2. Okay, so our left endpoint rectangular approximation. Our left hand rectangular approximation is 21/2. Okay, so there you have it. Thanks so much for taking the time to watch this video. Please feel free to subscribe to my channel by clicking up here so you can get updates to the subsequent parts of this integration review series. More videos can be found on mathserve.com. Thanks again and have a wonderful day.